Hello and welcome to the 8th lecture of this short course called Behavioral Theory of Systems with a view towards data-driven control. So, in the last lecture we were discussing about the benefits of having the system of equations in the upper triangular form, and we saw that just like in the case of linear equations, system of linear equations, once you have this upper triangular form, you can solve the last equation first because it's a standalone equation involving only one unknown variable, and then you can use that solution to get the solution for the next but one variable using back substitution, and then use these two further to get the the third last variable, once again using back substitution. And you can do this back substitution from bottom up to get the full solution, right? Now this process required, for linear equations it's very easy, but for the kind of equations that we are dealing with, namely ordinary differential equations with constant coefficients, ordinary linear differential equations with constant coefficients, it requires us to also have knowledge of how to solve the standalone linear ODEs, and then with one variable and then with several variables with single standalone equations. So in this lecture we'll try to see, we'll brush up your memory as to how to solve this standalone equations involving either one unknown variable or multiple unknown variables, but scalar single equations, right. So we start with one variable case. So we have a polynomial p d dt w equal to 0. We have been using xi for that, so that's what we are going to continue using now. P xi w equal to 0, right, where this p xi is a given polynomial. Of course, the behavior in this case is the kernel of this polynomial, right, isn't it? How to solve for this? This polynomial will have a shape in general which would look like p n xi to the n plus p n minus 1 xi to the n minus 1 and so on up to p 1 xi plus p 0. And you remember that this is like you have to find out the roots of this polynomial, and then the solutions are given by these various roots, but sometimes you also need some multiplication by some t to the power, what should I call it, t to the power mu. So these are the so called basis functions which give us the solution of this system of this equation, right. But why is this so? Why is this so? Let us try and understand that a little more carefully. This may be a repetition for many of you, but just still bear with us because it will finally clear up various things for us. It will be easier for us to proceed further, and in any case there is no harm in having a new point of view as far as these old things are concerned, right. Now to understand why is this so, we will first see the following very interesting fact about product of polynomials. Suppose I have two polynomials p xi and q xi, and suppose that p and q are co-prime. What do we mean by co-prime? It means that they do not have any common divisors apart from constants. In other words, their GCD, okay, I should not write it this way, p and q as a pair is co-prime. It means that the GCD of p and q is just 1, all right. In that scenario, if you look at this product, the claim is as follows: kernel of the product You look at this product and look at the kernel of this product. That is kernel of P psi, direct sum kernel of Q psi. It's fantastic, right? The kernel of the product, that means the solutions of this product equation P psi Q psi. So the product causes a function to go to 0 if and only if the function can be written as a sum, as a unique sum of two trajectories W1, W2, where W1 satisfies P psi W1 equal to 0 and W2 satisfies Q psi W2 is equal to 0, right? Now, why is that so? Why is that so? Okay. So, first thing that we notice is that So the first thing that we notice for this case is that recall P psi and Q psi, this is co-prime, right? We have assumed that this is co-prime. That means that GCD is 1. Now, once again go back to Aryabhatta-Bezu identity. What does it say? It says that there exists a polynomial A psi and another polynomial B psi, okay, such that A psi P psi plus B psi Q psi is equal to 1. Now, this is an identity, right? That means, you see, these i's are placeholders, right? So because it's an identity, if you place anything in the placeholder's position, it should still be true. In other words, if xi were to be just d dt, still it would be true. Yeah? This is not an equation, this is an identity. Be very careful in making a distinction between the two. This is an identity. So it doesn't matter what this placeholder is actually, it will be true always. Yeah? Like for example, if I have d dt plus 1 the whole squared, it will always be equal to d squared dt squared plus 2 d dt plus 1. If you put your name here and allow the algebra generated by your name, the polynomial ring generated by your name, it will still be true. This is an identity. Likewise, this is an identity, which means now functionally, if I make W, if I make this left hand side act on W, I should get back W because this is actually 1. So, A psi P psi W plus B psi Q psi W must be equal to W for any trajectory W. Now, for any trajectory W now, this is true. Now, suppose I make okay, now notice first thing. So somebody gives me a trajectory W. I write W as A psi P psi W plus B psi Q psi W. Okay? Now, notice this guy. I call this guy to be W 2, I define this to be W2 and I define this to be W1. Suppose W, this is true for any trajectory, right? Now suppose in particular W belongs to the kernel of the product, W belongs to kernel of P xi Q xi, okay? In that case, if I make Q xi act on the W2 that I have defined, it's going to be Q xi, A xi, P xi, W, right, because W2 is defined like that. Now these are differential operators, polynomial differential operators, they commute, right. It does not matter which differentiation you do first and which differentiation you do second. Like for example, if you have d dt plus 1 times d dt plus 2w equal to 0, whether you do this differentiation first and then this, or you do the other way around, d dt plus 2 d dt plus 1 w, it does not matter, the two are exactly the same. So they commute. Because they commute, I can write this as A xi, P xi, Q xi, W. But W is in the kernel of P xi Q xi product, so this must go to 0. A xi acting on 0 will produce again 0, so this is 0. So indeed you see W2 belongs to the kernel of Q xi. Do exactly same exercise and you can prove that this guy belongs to kernel of P xi. So do you see that every trajectory W which is in this kernel can be written as a sum of W1 and W2, right, which is such that W1 belongs to the kernel of P and W2 belongs to the kernel of Q. So what have we proven essentially? We have proven that kernel of P xi Q xi is contained in the kernel of P xi plus kernel of Q xi, right. Anything that is here would automatically be here through Aryabhatta-Bezu identity essentially, yeah, because of this construction. Now, is this containment also true, right? In fact, it will turn out to be true because suppose we have a W1 and a W2. It's easy to see that if I do this P xi Q xi multiplication to this guy, which is like P xi Q xi acts on W1 plus W2, that is equal to P xi Q xi W1 plus P xi Q xi W2, but W2 belongs to the kernel of Q xi, so this goes to 0. P xi acting on 0 trajectory produces 0. This once again using commutativity, this is the same as Q xi P xi W1, but W1 is in the kernel of P, so this goes to 0. So overall you get 0. So in fact this containment also is true. So what we have essentially is that the two are equal. What is left to show? All we have left to show now is to show that it's a direct sum. Now if you recall your linear algebra, you know that a sum becomes a direct sum if the intersection is 0. So all we have to show now is that kernel of P xi intersection kernel of Q xi is just the 0 trajectory. How do we prove it? Prove by contradiction. Suppose not. Suppose kernel of suppose there is a W which belongs to both these kernels. It's killed by both of them. It's here. It's also here. Okay. Then what do we do? Once again, Aryabhatta-Bezu identity comes to our rescue. Because of Aryabhatta-Bezu identity, I know that and because of the fact that PQ are co-prime, we know that A xi times P xi plus B xi times Q xi, sorry, xi, yeah, acting on this W must be equal to 0, right? Because W belongs to the kernel of P, so this part goes to 0. W belongs to the kernel of Q as well, so this part also goes to 0. So overall it's 0. But then that's a contradiction. You see why? Because this is identity, this is 1. This implies 1 times W, which is of course W, that is equal to 0. So you assume that W is in this intersection and you infer that then W must be 0. So that means this intersection must necessarily be just the 0 trajectory. So we have kernel of P xi Q xi product is equal to kernel of P xi direct sum kernel of Q xi. Lovely, no? Now you might think that what does this even mean? How does this even help? There is some observation, but how does this help as far as solving for a general differential equation is concerned? That's what we wanted to do, right? We wanted to solve for an equation like this. But now, see, what is happening here is the following. The moment we have this, now once again we go back to algebra. So somebody gave us this polynomial, right? This is done here. Now I'm starting with the general polynomial that was given to us. I have B given by kernel of some polynomial P xi, right? Now what we know from algebra, from in fact the fundamental theorem of algebra, it says that polynomial P xi over complex numbers factorizes into linear factors. Yeah, you can write this as xi plus lambda 1 to the power mu 1 times xi plus lambda 2 to the power mu 2 times dot xi plus lambda k to the power mu k. Yeah, and we know that these factors are co-prime. So what I can do is now I can apply this result repeatedly, that when they are co-prime I have this is my lemma, I apply this lemma repeatedly to obtain that when I have a product like this, the kernel of this product is equal to the direct sum kernel of xi plus lambda 1 to the power mu 1 direct sum kernel xi plus lambda 2 to the power mu 2 direct sum direct sum kernel of xi plus lambda k to the power mu k. Lovely, right? So now look at these structures, they look all similar. Once I know, of course I have admitted these lambda i's from complex numbers, right? Yeah, that's the fundamental theorem of algebra, that over complex numbers every polynomial factorizes. But you see, because we are dealing with real polynomials, these complex numbers, these complex roots will appear in complex conjugate pairs and you can club them to get real factorization. Only thing that you have to allow is that not just linear, but you have to allow for quadratic factors as well. That will go to you as an exercise, yeah, how to do that for the real case. But in this main lectures, we are going to consider this to be complex numbers because it makes our life easier. Right. Now once I have this, all I have to do is I need to find out how to parameterize solutions of polynomial differential equations that look like this. There are only one singleton root of multiplicity mu. How do you get solutions for this? Right? And their solutions are of this type. Let me just write it down and you then verify. Yeah, the solutions are given by so this behavior, suppose this is my behavior, then behavior will turn out to be the span of e to the power minus lambda t, t e to the power minus lambda t, t square e to the power minus lambda t dot 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 e to the power dot 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 t to the power mu minus 1 e to the power minus lambda t. What you have to show, that goes to you as an exercise. I am not going to do this. Exercise, prove that these vectors linearly independent over C, okay, and linear combinations and this fact essentially that B, that the behavior B, which is kernel of this, is in fact exactly equal to the span of these vectors, these trajectories. Right? Should not be difficult for you. If you have done rudimentary linear algebra, you should be able to do that. I mean, one can easily see already that, you know, if you just look at these guys, these guys to be linearly independent, that means you take any linear combination of that. Yeah, if that is 0, then all those coefficients must be equal to 0. Right? What does that mean? It means that if you have something like a0 e to the power minus lambda t plus a1 t e to the power minus lambda t plus dot 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 up to a mu minus 1 t to the power mu minus 1 e to the power minus lambda t. If this function is identically 0, then these numbers must necessarily be 0. Yeah. How can you prove this? Well, just you can just notice that this is this polynomial a0 plus dot 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 plus a mu minus 1 t to the power mu minus 1 is times e to the power minus lambda t. This is identically 0 for all time. Okay. And then you just need to do something like take t equal to 0. Yeah, if you take t equal to 0, then this is 1. All these guys will go away. You will just have a0 equal to 0, right? And then you can continue like that. It's an interesting exercise. Why don't you do it on your own and see what happens, right? It's an interesting exercise. So do that. And then you have to show that a general expression like this satisfies this differential equation. That is also very easy. So every expression like this satisfies this differential equation, which means this is true. This part is a little difficult, that you have to show that these are the only possible trajectories that can satisfy these equations, right? It's a little complicated, but do that. It's a nice exercise. Now, once you have that exercise, once you have done that exercise, you realize the following thing. Once again, I'm going to use some terminology from linear algebra. If you have not done linear algebra or have forgotten details of linear algebra, it would be a nice time for you to go back and refresh your memory about linear algebra. Okay, so dimension. I'm sure you have heard of this term. Those of you who have done linear algebra and those of you who have not will know this term, dimension of a vector space. Dimension of a vector space is namely the number of vectors in a basis, right? So the dimension of kernel of psi, what would that be in that case? what is this basis? What is the size of this basis? What are the number of vectors in the basis? 1, 2, so t to the power 0 to t to the power mu minus 1. How many? Mu, of course, mu is the degree. So, the dimension is in fact degree of p xi. And then if you go back to this result where I have added these guys up, this direct sum, you see what is the degree of the polynomial p? The degree of the polynomial, so the polynomial p is this product. So, the degree is the sum of these products. So, mu 1 plus mu 2 plus mu k. So, the degree of this polynomial p is equal to summation mu I going from 1 to k, correct? And now because it is a direct sum, the dimensions would add up. So, the dimension of kernel of p for the general case, dimension of kernel of p xi is equal to sum of dimension of kernel of xi plus lambda I to the power mu I going from 1 to k. This already says that this is equal to mu I. So, then this is equal to I going from 1 to k mu I, but that is equal to degree of p xi. So, what we have established is that dimension of kernel of p xi is equal to degree of p xi. Great, right? Okay. Now, this can be used to infer something interesting. Remember the question that I had asked, that two row spans equal implies the behaviors are equal. The behaviors are equal. We were asking the converse question, is this also true? Well, at least for this very special case of scalar singleton equations, it should be true. Why? You see, because of this following reason. Suppose, so I will prove these two things first, and then it will automatically follow. This implication will automatically follow. So, first suppose I have kernel of p1 xi is contained in kernel of p2 xi, right. This should imply p1 divides p2, right. Is this true? Let me check. Right, p1 should divide p2. Why is that so? Let us see. Once again, proof by contradiction. Suppose not. Suppose that is not true. That means p1 does not divide p2. That means what? I can write p2 xi as some q xi times p1 xi plus r xi. This is Euclidean division with remainder, such that the degree of r is strictly less than degree of p1. Okay? Now, I will get rid of the xi's. Just write this p2 equals q times p1 plus r. Now, take a vector from kernel of p1 and make it act on it. I have w, 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 where w belongs to the kernel of p1. What does that mean? That means this will go to 0, right, but I also have kernel p1 contained in kernel of p2, which means this will also go to 0. So, that means what we are left with, we are having r xi w equal to 0 for all w in kernel of p1, but that is a contradiction. Why? Because this says kernel of P1 then is contained in kernel of R psi, that is a contradiction. Why so? Because if this were so, then this is a subspace of this. If it's so, if it's a subspace, then the dimension of kernel of P1 psi must be less than or equal to dimension of kernel of R psi. But what is this dimension? This dimension is degree of P1. What is this dimension? This is degree of R, we have already seen. And this is what the situation is, right? Degree of R must be strictly less than degree of P1. But here I am saying the degree of P1 is less than or equal to degree of R. That is a contradiction. Yeah, that is a contradiction. Absurd. Reductio ad absurdum. Now we have reduced the situation to something that is abstract, patently abstract. Yeah? So this can't be true, which means now what is not true? So we had started with this, no, that suppose not. That has led to this absurd thing. So that means this is where we went wrong. So in other words, P1 must divide P2. Likewise, so kernel P1 contained in kernel P2 implies P1 divides P2. Likewise, kernel P2 contained in kernel P1 would imply P2 divides P1, which means if kernel P1 is equal to kernel P2, then that should imply P1 divides P2, P2 divides P1. What does that mean? One divides the other means they differ only by a constant multiple, which in other words means that the span of P1 is equal to span of P2. These are called ideals. The ideal generated by P1 is equal to the ideal generated by P2, which is the row span, right? This is all possible multiples of this is equal to the set of all possible multiples of P1 is equal to the set of all possible multiples of P2. So you see, we have proven this converse question. This converse is true, at least for this very special case of scalar equations. Is this true in general? Well, as we will see soon, it is also true in general, right, for C infinity functions. That and many more is what we are going to see in the next few lectures. Till then, take care. Bye.